Accelerating SOC verification using process automation and integration. Abstract. As the competition in the smart device industry is getting fierce, the importance of a TAT, turnaround time, reduction in SOC, system on chip, development increases dramatically. The proposed system that could combine the disciplinary workflow together, automated execution, explore the tested result, and check if the design verification issues are satisfied with the required criteria. The system enables us to users manipulate and configuration users process steps with the parametric input-output data and the automated multiple simulation emulation scenarios, and as a result, it is expected to greatly improve efficiency of SOC development process by reducing annual errors and accelerating product design. Introduction. While TAT reduction gets more important and difficult, the size of the complexity of SOC increases as well, meaning it is getting harder to meet TAT on time. In order to meet TAT on time, SOC is broken into sub-blocks. In addition, the overall SOC development process is divided into three sub-processes. The first phase is the IP-level design and verification. The second stage is block level, which includes various design and verification stages. The last stage is the top level and full SOC level design and verification stages. As the SOC project and development processes are divided into sub-parts, more manpower and effort are required in SOC project. In general, the test benches are developed for functional verification in every design and verification stages. Regression tests are followed by the functional verification. Suitable input and outputs are produced while regression tests are performed. Design and verification engineers who are in charge of their own blocks develop and run their own scripts and application in order to automate the design and verification process. The script files and applications are developed and tested in users' developed environments as described in Figure 1. As the complexity of SOC design increases, it is becoming a more difficult and tricky job to manage the increased number of the user-specific development environment. Figure 1. Various scenarios by developer, verification engineers, project, and team. In this paper, a system for design verification process automation and integration is proposed to improve efficiency in a collaborative work process in SOC design. 2. Related roles. A. Continuous integration. In a collaborative project, there are source code files generated by developer involved in the project. When a source codes developed by a developer are merged into a project, there will be some critical problems. The problem may not be executed successfully because of inconsistent development environment throughout the developers. Another problem is an inconsistent version of control. Continuous integration is a concept of preventing inconsistent development environment and version control problems. The most commonly used tool is Jenkins. Figure 2. Continuous integration flow of Jenkins. The continuous integration flow of Jenkins is shown in Figure 2. First, all developers share all source codes through version control system and or the other configuration management tool. Jenkins takes the code from the version control system, checks failures and errors, and downloads relevant libraries from the repository, and then Jenkins runs test scenarios to check if the source codes are correctly programmed. Only if the test scenarios are done successfully, the source codes are released to the operating servers. B. Triage. Triage is a military medical term, which means the process of classifying a scheduled patient by their injury severity. Nowadays, This term, triage, has been widely used in IT, information technology, and the business industries. For example, an IT operator department triages issues to decide which problems are urgent to most. The top priority issues are handled as soon as they arise, and the issues in a medium priority arise when there is no issue with a higher priority than themselves. If there is no medium property issues, the low property issues are handled. However, in the worst case, low priority issues might not be dealt unless their priorities are reassessed as a higher priority level. It's crucial to deal with a high priority requirement as well as soon as possible to meet the project plan on time. In agile software development, requirements are typically triaged at the first of each iteration. Because an iteration is a short development cycle, it's crucial to deal with the higher priority requirements quickly to ensure that they are satisfied in time. In this paper, the term triage is used for priority of failures and errors. Failures and errors are triaged by some criteria, and debugging failures is performed based on the priority, which is a result of a triage. C. SOC design and verification flow. The design and verification of the SOC hardware start at the SOC specific stages as shown in Figure 3. It proceeds in a sequence of an IP development, block development, and SOC integration. Not all processes are performed in a strict sequence manner, meaning the order is not a tail-to-tail sequence. Instead, some progresses can be overlaid and proceeded in parallel. The development of the IP is carried out in accordance with the SOC development schedules. As the IP development begins, the verification of the IP starts, which IP will be used in progress of determining the specification of SOC, and which version will be used in SOC. In addition, the block configuration is determined according to SOC specification, and block development is used. Block design and verification includes an inter-IP connection in the block and functionality of the block. In parallel with this, inter-block connection starts at the top SOC perspective. During the connection of the inter-block, design of SOC top module functionalities are followed. Figure 3 shows this process over time. This paper defined verification steps for each development stage and defined them as verification level. In VR1, IP level design verification is performed, and a block level design and verification is started following. In VR2, IP level design and verification, block level design verification are mainly performed, and design and verification for SOC top is started. IP level design and verification is done before VL3. In the VL3 and BF4, the design and verification of blocks and SOC is mainly performed. The difference between VL3 and BL4 is the regression test. In BL4, regression test for blocks and SOC is performed mainly. Figure 3, SOC design and verification flow level. 3. Proposed system. This paper proposed the integration of the design verification environment and each processes. There are 3 methods to integrate the design and verification processes: a top-down method, a bottom-up method, and a hybrid method of a top-down and bottom-up method. This top-down method is forcing current environment, the processes, and integrated into a unified one. And the bottom-up method creates an interface to unify various kinds of development environment and the processes while preserving the current developed one. The hybrid method is a mixed one of the top-down and bottom-up method. The ultimate method of integration is the last third method. On the first trial of integration, it is hard to step into the first and third method directly because of verification stability and risk. For that reason, this paper adopted the second method that is based on the bottom away. Another reason is the current verification environment has long been optimized for each verification engineers and each verification unit. The environments are already optimized in many parts of each unit, but there still remain efficient parts. It is expected that many of remaining efficient parts can be efficient as they are integrated into platform proposed in this paper. Another main idea of this paper is automation. While the basic processes of current design and verification are preserved, the proposed system maximizes the efficiency of the building environment for design verification by automating manual tasks. The quality of the verification environment can be maintained high and can be built quickly by removing errors which are caused by human errors. In addition, the flow needs to be changed. The change can be handled more flexibly. The proposed system could be settled down as a standard workflow out of the traditional verification methodology guidance. In this paper, the system is focused on each verification level of the SOC verification. Many design and verification environments are diverse in each design stage, such as IP, block, and SOC level in actual SOC project. Each design unit and the design team has their own well-structured workspace, such as directory structures and verification types. In the same design stage, some standardized workspace structure can be created. However, it is very difficult to standardize workspace structure in different design stages. In order to integrate the design verification environment, it's preferable to support all environment rather than formalizing all stages of environment. In this paper, 5 modules were developed in shown in Figure 4 to integrate and automated version various verification environment. The first module is Flow Controller. Figure 4, integrated platform and internal queue for automation and verification. Flow Controller. Flow controller system is that a unified and automated workflow that exists in each team and step of verification stage, and it is similar to existing continuous integration (CI) services while the controllability of workflow has been improved. This is because during the SOC verification period, various workflows are integrated into proposed automation system. The proposed system treats each workflow as a unit of work. A work consists of a sequence of steps where a step is predefined execution commands or operation. A sequence of steps is defined as a scenario. A scenario starts from start steps and ends at the end steps. There may be several steps between start steps and end steps, which are defined as normal steps. Each step has a link information, header IP and tail ID, that connect to each other. Furthermore, each step is divided into 3 steps of pre-body, and post-step. On the other side, only the body of the step is visible, and pre and post step is responsible for the operation to supplement the body step. The scenario and the steps are reusable. The operation of each step can be determined at the time the workflow applied to the action is executed. So, we can insert various continuous input set even if they're using the same step and the scenarios. Figure 5 is an example of actual step and the scenarios used. Figure 5, verification automation script and scenarios and steps. 2. Regression manager. Regression manager is a system of regression test steps for managing and control and leverages internally developed queues and commercial regression tools. Currently, a third-party tool used in Samsung has been integrated. In the IP stage, the regression environment engine configures as a script, and information in this part is reported through the metadata. In the IP level design stage, the regression environment is configured by a script, and the information on this is reported through metadata. A large amount of jobs provided by regression managers and information of their status and results can be checked at a glance because those information can be connected by data structure managed for each scenarios. 3. Job scheduler. Job scheduler is schedule jobs based on a priority or reverse the time to execute reservation time. It is internally developed. In the job scheduler developed in this paper, the basic unit of the job is composed to scenario. One job is submitted to the job queue with one scenario. A job preferred to when certain conditions are satisfied. The unit of the execution of each job is group of each entity called actors and is parallel for load balancing of service group over daemon. Several daemons will perform a job coming into their actor group. All jobs are performed while the start, step, and the step of the scenario are continuously managed during the execution. Each job has a status information of a scenario and the status information of each step and control lifetime of a job with the status information. Figure 6 shows the real-time status of various types of scenario, which is managed through the system proposed in this paper. Figure 6. Job status managed through automation system. The triage scenarios. Triage scenarios TS module is classified issues and failure based on data generated from regression. For example, if a bug or failure occurs while any jobs are executed, TS has several algorithms to narrow down a region of a target range of possible issues dynamically. It also relearns if necessary to provide sufficient information for designers and verification engineers for rapid debugging. In the current version, the binary search algorithms and machine learning clustering are implemented. Our proposed system collects many regression test results and creates clustering data for each block of density-based clustering techniques, which can be reordered a bunch of the test cases for efficient verification. It has a test schedule to reorder the test list for error cases per cluster. The reasons to why we are applying those solutions are two things. Firstly, when design data changes, it makes too many tests to perform every particular period of time and resources inefficiently. Secondly, since the test cases for verification, each change blocks are connected to different blocks and affect each other. The error case that occurs is not only failure of the test case, but also potential error element. If you connect it to a strategy to verify it in advance, you can expect to improve efficiency and verification speed. 5. Data Manager. Data Manager collects all data while every job execution and uses them for further analysis. For example, all design changes, especially RTL changes, are collected over the SOC development cycle and are used to correlate it with the simulation failures to assist verification engineers to debug those failures. The data manager implemented in this paper can integrate the verification information for each IP block. SOC verification stage and interwork with the verification information for each stage. A verification can be efficient through the interworking of the verification information. The information that is integrated in the data manager is a verification task for each verification step and the result information for each verification operation. These data are formatted and stored in the database, and the user input information and the log information for each step are stored in a disk in the form of a file. The meta information for the abnormal data is formulated and managed. The formalized meta information is summarized using the mutual relationship. The verification information accumulated in this way can be different verification stages, and the link to information leads to the high efficiency of the verification. The verification status of each stage is transferred to the verification manager through the dashboard system and the mail alarming service. Figure 7 shows the dashboard system and the email reporting service. In addition to the ongoing research is informatizing the amount of the change in the design information of each stage of development. It's expected to shorten the verification period and increase the verification quality by linking this verification information. Experimental result. The integrated platform is applied to our design verification and verification to automate the regression. The experimental result is shown as below. Until now, the verification work for each project has been classified as a role of each level as a verification engineer. In other words, the work was independent of each other. Verification for each IP and block level was repeated or added every time the development version was changed, and it is being processed separately because it was not synchronized to top level verification. Automation and the information integration of each verification phases can optimize the verification flow and the test for each event. In order to calculate the effect on a number of verification efficiency generated by each verification step was written and viewed. It, of course, will be different for each IP block and the SOC product, but the verification time according to the complexity has been quantified by referring to the result of actual project. The table 1 shows the experimental result. Experimental number of comparative result of the verification time between the existing method and the proposed test plan. A, B, C mean the verification time for each verification time. A1 is the verification time in the existing IP level verification. The verification time of the proposed platform can be defined as the maximum value of the A or B or verification time used for failed cases in IP verification or verification time used for the failed cases in block verification. At the VL1, A1 is defined as 4T and B1 is defined as 60T. The existing verification time becomes 20T, and the proposed platform application result could be 16T when a failed cases are not happening in the IP or block level. At the VL2, all levels of verification tests should be conducted, so the verification time could be reduced to max run time along A2, B2, D2 test running time compared to the previous sum of each level. At the VL3 and VL4, verification time is reduced by a max run time of each level, analyzing the time for the failure occurrence of statistically probability is not clear from the differences in the distribution by verification time. Thus, it will be interpreted as approximation through the actual application. Table 1, verification time by each verification steps. Figure 8 shows the results applied to the actual project. This result shows efficient fault verification time before and after each verification step. For reference, it has not been applied to the overall verification of the actual project, has been applied to the some IPs and the corresponding blocks, and in the top level of SOC has all been applied. At the tier 1, as mentioned above, the verification time is reduced by around 35% and the verification time is reduced by the 43% at the VR2. At the VR3 and VR4, verification time is reduced by 28% and 27% separately, respectively. The verification time reduction in VR3 and VR4 is less than that VR1 and VR2 because it does not include the time reduction effect of the IP level verification. The verification time for each step was decreased by up to 43% when the triage flow in the integrated platform applied to the test failure cases at each verification stage at figure 3 at the figure 3 shows. Okay, the figure 8, reduction of verification time by each verification steps. The conclusion, in order to provide a verification environment which is optimized for complex SOC, each verification workflow process is being automated for each target design level. Furthermore, verification time can decrease and verification quality can increase though these processes are integrated into automation environment. The main idea is to integrate the existing flows and a verification environment so that they can be reused in the form of the platforms. These integration platforms can enable verification environment to set up rapid and can unify the scattered information of each verification level. Furthermore, the unified information can enable to optimize the verification environment. In this paper, a platform for automating and integrating workflow scatters by stage for each verification target was proposed to shorten the verification time. In the actual flagship mobile app SOC design project, many local workflows from IP verification to block and SOC verification were integrated into the proposed platform to verify the maximum 43% of the verification time per step. To this end, some of the existing unautomated workflows have been automated and verification data has been linked to the integrated system. The integration of each department has not been proceeded. In addition to the part where each verification phase information is linked to the efficiency as number of the tests was reduced by automating the execution of the processes and the workflow and applying to the triage and proposed triage ratio to the case where the verification status and information were integrated. The verification time could be greatly reduced. This reduced time helped to improve the quality of verification because it can be used for additional verification. Moreover, the proposed system has greatly reduced the effort to create an integrated platform because it can reuse the existing workflow, the verification environment, and the existing system. In conclusion, the verification information distributed and produced at the verification stage could be integrated into one view through the proposed data manager, and the integrated information could be analyzed and utilized to optimize the verification environment. These results resulted in reduced verification time and improved verification improved verification quality. Through additional research, we plan to reorder the test list of error cases by clustering each block by density-based clustering using a lot of regression test result information for each verification phase. In addition, we would like to consider using the classification model to determine the group of sanity tests for error cases. In addition, we expect that the additional applying to the dynamic distributed structure technique of job scheduling algorithms, the verification system will be improved to shorten the verification time. Thank you. Thank you for your time for reading, writing, exercise using process automation and innovation. Thank you. See you next time.